All right, let's dive right into this explainer. You know, when you settle into your seat for a long flight, buckle up and feel that immense power during takeoff. It is so easy to assume the humans up front are manually tweaking every single engine setting and physically steering the whole way. But the reality of modern aviation relies on a digital partnership that is just absolutely fascinating.
So who is actually flying the plane? It's kind of a mind-blowing question, right? Because while the human pilots are undeniably at the helm, the true digital brain doing the heavy lifting is something most passengers will never even see. We're talking about a system so integrated and so essential that without it, the incredible fuel efficiency and safety records of modern air travel simply wouldn't exist. To make all this accessible, here is our visual flight plan for today's explainer. First, we'll meet the digital co-pilot, then look at the anatomy of the FMS, check out the pilot interface, walk through the actual phases of the flight, and finally wrap up with the redundancy and safety systems. Let's get into it. All right, section 1, meet the digital co-pilot. Let's look at what this tech actually is, and maybe more importantly, why the aviation industry felt they desperately needed to build it. The star of our show is the Flight Management System, or FMS. Why did they develop it? Well, airlines had a massive need to squeeze every drop of efficiency out of their fuel, drastically cut down the workload on the flight crew, and ultimately lower operating costs. Think of the FMS as the ultimate digital co-pilot. It seamlessly combines navigation, performance management, and flight planning to give incredibly precise 3D guidance along the plane's entire route. To really appreciate this, look at the leap from the old technology. Before the FMS, aircraft used something called the Performance Data Computer System, or PDCS. But honestly, the PDCS was basically just a really smart advisor. It would tell the pilots, hey, here's the best engine setting, but the humans still had to do the manual tweaking to get that efficiency. The FMS? Totally different ballgame. It hooks directly into the thrust and flight controls. It literally takes the human out of that manual loop, taking full automated control over both the vertical and lateral flight paths. Moving on to section 2, anatomy of the FMS. Now that we know what it does, let's pop the hood and see how this thing is actually wired together. Think of the Flight Management Computer, the FMC, as the central brain of the whole operation. And branching out from it, these AirInc data buses, they act exactly like a nervous system. You've got sensors pulling in air data, engine controls monitoring thrust, radio antennas like VOR and DME. All these different parts are just constantly firing data back and forth across these buses to keep the flight exactly on track. Now, to juggle all that information without crashing, this computer relies on 3 highly specialized types of memory. First, there's bubble memory. This is essentially a giant vault for all the bulk navigation data and aircraft performance specs. Then you've got CMOS RAM, which handles the immediate stuff, holding the specific active and secondary flight plans pulled from that vault. And finally, a UV-PROM holds the actual operating program, basically the core operating system. Here is a crazy detail though. That bulk navigation database, it isn't static. Aviation routes and airport procedures are changing all the time, so the system absolutely requires updates on a strict 28-day cycle. And how did they update this ultra-advanced digital brain? Originally, it was done with magnetic tape. They would literally push a tape cartridge into a portable loader, plug it into the computer, and transfer the fresh data, so the plane's routes were perfectly accurate for every single flight. Okay, section 3, the pilot interface. Let's talk about the human-machine connection. Where does the pilot actually sit down and collaborate with this computer? That happens right here at the Control and Display Unit, or CDU. This sits right in the center console between the pilots and serves as the mouth and ears of the digital co-pilot. You've got an alphanumeric keyboard for typing, special function buttons to change modes, and line keys running down the sides of the screen so the crew can select specific commands or review the flight plans. And I find this just mind-blowing. The entire vital input for a massive commercial jet goes through a tiny, flat-faced CRT screen that measures just 2 by 3 inches. On that tiny screen, it flawlessly crams 24 characters across 14 lines. It's incredibly efficient. Small characters show default or computer-predicted values, which pilots can actually overwrite if they need to, and large characters show data the flight crew actively typed in themselves. The real magic happens down on the bottom line, line 14. That's the scratch pad. If a pilot wants to change, say, their cruise altitude, they type the number into the scratch pad first, then hit the adjacent line key to bump it up onto the screen. But the most important button on the whole board? The exec, or execute key. A pilot can build out a whole new temporary plan, but the plane keeps flying its original route until they hit that exec key. Once pressed, a little bar lights up to confirm, and boom, that new plan is officially active. Section 4. Phases of the flight. Let's trace how this all comes together on an actual real-world trip, from takeoff to landing.
When the pilot hits the perf key, they open up the performance pages. And as you fly, the system literally scrolls through different phases automatically. It starts with TO for takeoff speeds. Once you're climbing, it flips to the CLB page. Hit your cruising altitude, it swaps to CRZ, constantly crunching numbers for your arrival fuel and time. Start heading down, it hits DES for descent. And finally, right when the leading edge slots extend near the runway, it flips to APPR for approach. And the entire time, it is autonomously tweaking the engine thrust and pitch to guarantee you get maximum fuel economy. It's brilliant.
Of course, flights rarely go exactly to plan. Air traffic control redirects you all the time. If a pilot adds a new waypoint mid-flight on the start data page, the system flags it with a TMPY legend, meaning temporary. And here is the cool part. Before you can even hit that execute key, the computer rigorously double-checks your scratchpad entry. If you type something invalid, it literally flashes error and turns on a warning light. It's a hardwired safety net that stops bad data from ruining the active flight plan.
Finally, Section 5, redundancy and safety systems. We have to ask the most critical question in aviation. What happens if this super complex computer just fails while you're thousands of feet in the air? Well, as you'd expect, the engineering here is rock solid. Airplanes actually have two completely autonomous FMC systems installed. Normal conditions, these two computers are constantly sharing and verifying each other's data over that data bus in a process called crosstalk. A pilot can even use their offside system to review or build a temporary plan without ever disturbing the active one flying the plane. And hey, if one entire computer completely dies, the pilot simply switches their display unit to tap into the surviving computer. Uninterrupted safety, period. It's just incredible when you think about the processing power and the sheer level of integration housed in these systems. So I want to leave you with this final thought to ponder as we wrap up this explainer, considering how much the flight management system already handles, from perfectly tracking fuel down to the exact drop, to calculating complex 3D descents. How close are we really to an era of totally pilotless commercial flights? The digital co-pilot is already doing the heavy lifting. Maybe that final leap isn't as far off as we think. Thanks for joining me for this deep dive, and keep questioning the incredible hidden systems running our world.